Hello everyone, good afternoon and welcome. Today I will be discussing the possibility of implementing vacuum assistance into our high pressure die casting processes here at the Imaginary Company. I will explain the process, why it's used, the advantages it carries over conventional die casting, and its limitations that should be taken into consideration when implementing vacuum mechanisms. I will also be assessing this process's manufacturing readiness level to determine its maturity, whether or not it's ready to implement. So here's a little background into what our current situation is like here at the Imaginary Company. We are still utilizing conventional and outdated high pressure die casting techniques here. Conventional die casting is unfortunately susceptible to producing castings of higher porosity due to the entrapment of air during the metal injection. This presence of gas porosity is especially harmful because it can cause adverse effects on our product's material properties, weldability, and pressure tightness. In turn, this may cause increases in customer dissatisfaction, which we try so hard to avoid. As luck would have it, there's a way to solve this problem. Vacuum-assisted die casting implements a vacuum into the casting process, which completely eliminates the gas porosity in our castings. By creating a much lower atmospheric pressure in both the shot sleeve and the die cavity, much less gas will be entrapped in the molten metal. The figure below shows approximately how a vacuum will be added to the die casting process, the specifics of which I will discuss in just a few minutes. And now a little bit on how this whole process will work for us. I have images here outlining the 7 steps of the vacuum assist process. The figure on the right here is step 1. The melt is filled into the shot sleeve at the bottom right. The air pressure in the mold cavity, which is labeled with a C, is currently atmospheric pressure. The mold is closed and the vacuum valve, V, is operational and ready for use. The vacuum pump, labeled with a P, ensures optimum and consistent values in the vacuum tank, which is labeled with a T. Now in step 2, the plunger, A, moves forward. A signal is sent from the die casting machine to the vacuum system, activating a timer. The air pressure in the mold cavity slightly increases. The vacuum valve is in standby mode and the evacuation plunger is in open position. The timer is in operation and the vacuum is switched on as soon as the plunger passes the filling opening. The tank is empty and the vacuum release valve, labeled with an O, is in closed position. In step 3, the plunger has passed the filling opening. The timer sends the vacuum start signal to the system. The vacuum release valve is now in open position. By means of force venting, air and gases are drawn out of the shot sleeve and the mold cavity, and they are introduced into the tank through the vacuum tube. The valve is still in standby mode and the air and gases escape through the evacuation plunger. The system measures the generated vacuum quantities in the mold cavity in real time. Step 4. The melt reaches the end of the sprue and the die casting machine switches to mold filling speed. The air pressure in the mold cavity slowly reaches its maximum value. The vacuum valve remains in standby mode to enable the air and gases to pass through. The release valve remains in an open position. In step 5, the velocity of the plunger increases. The first half of the mold filling phase is now reached. Thanks to the high venting capacity of the vacuum valve, an underpressure is kept in the mold cavity during injection. The vacuum valve is in standby mode, however it's ready to be activated by the energy of the middle flow. Step 6 shows the mold cavity now completely filled and the melt reaching the vacuum valve. The locking mechanism of the vacuum valve is triggered by the kinetic energy of the metal flow in a millisecond. The final pressure of the die casting machine ensures optimum filling of the melt into the mold cavity. The running melt at the front is stopped by the vacuum valve, and the vacuum evacuation cycle is stopped. Now in the final step, step 7, the mold is opened after the solidification time has elapsed. Simultaneously, the die casting machine sends a signal to the vacuum system, and the vacuum release valve is closed. The vacuum system cleans and cools the evacuation piston of the valve with compressed air, and the contamination levels of the vacuum valve and filter are checked, and the next vacuum cycle can begin. So the advantages of adding vacuum capabilities to our die casting machinery are quite numerous. As previously mentioned, the reduced porosity in our parts will greatly increase the mechanical, static, and dynamic properties of our products, as well as a much more refined surface finish and quality. Vacuum die casting also greatly reduces the back pressure of the cavity, and in turn we can use lower specific pressure, as well as alloys with poor casting performance that are typically unsuitable for die casting. The filling efficiency of the mold is much greater, allowing us to produce larger, thinner, and more complex parts with ease. On top of this, because of the decrease in the necessary casting pressure, the life of the tooling and mold is extended. The production efficiency of vacuum-assisted die casting versus the conventional die casting that we do now is almost negligible. Part rejection due to porosity and surface finish are also virtually eliminated. Of course, I'll be the first to admit that there are a couple of drawbacks to this process that I want everyone to be aware of. First of all, as one could imagine, there will be a high upfront cost of the equipment necessary to run a vacuum out of each injection mold unit. Manufacturing and installation are difficult, and the mold sealing structure is complicated, so it will most certainly be an investment. Secondly, the beneficial effects that I mentioned earlier will be negligible if the vacuum mechanism is not properly designed and controlled. The design of the exhaust position and exhaust area of the mold is critical. There's a critical area in the exhaust passage which is related to the amount of gas extracted in the cavity, the pumping time, and the filling time. When the area of the exhaust passage is larger than the critical area, the beneficial effects of this process are noticeable. However, if the area of the exhaust passage is smaller than this critical area, the gas may not be able to extract from the cavity fast enough, and you won't be able to notice the effects of a vacuum system. So now you may be wondering, what will this end up costing us? Well, like I said, there will be a bit of a pricey installation process. Of course, considering the numerous benefits that this will bring us, the price will be made up for in no time. Now, I wasn't able to find prices flat out stated online, but there are a multitude of companies shown here on the right that offer quotes on their products that I would have to email them about if we were interested. I've listed here a few companies. I think it would be best to start small with one or two vacuum assists to really get our foot in the door and see what the process can do for us before we dump a ton of money into it. And in terms of maintenance, it should hopefully remain at a minimum, as there are not too many moving parts that are quick to wear out. I would now like to discuss the concept of a manufacturing readiness level assessment. So MRLs are designed to assess the maturity of a given technology, system, subsystem, or component from a manufacturing perspective. They provide the decision makers with common understanding of the relative maturity and the possible risks associated with the manufacturing technology or product, in this case the vacuum assist process with respect to die casting. The levels range from 1 to 10, with 1 representing simply the basic principles being observed and reported, and 10 being a technology already formally tested and put into use in the industry. So now, how ready is vacuum-assisted die casting? Well, as it turns out, the manufacturing readiness level is absolutely a 10. In fact, it has been introduced to the industry and has been used widely across the industry for some time now. Now, this is good news to us because it means the process is very low risk to us as a company. Most of our competitors already utilize vacuum assistance in their die casting processes. This poses a threat to us as a company, considering our competitors are able to produce castings with a lower porosity and much less defective parts. So to sort of wrap up here and hammer my idea home, I would like to conclude by revisiting the main advantages that implementing vacuum assistance into our die casting process would have. Mainly, less porosity in our parts equals less defective parts, which equals less money down the drain. Also, less porosity in our parts also equals a higher quality part in terms of mechanical properties and surface finish, and therefore a higher customer satisfaction. Not to mention the filling efficiency of our molds and the lifespan of the tooling and mold are all greatly impacted. So I included the following citations to show where I got my information from and to evaluate the possible bias involved to ensure that I'm presenting this information to you in the most fair and unbiased way possible. My main source here is from the Foundry Lexicon, a sort of encyclopedia for all things metal manufacturing related. Now, this is where I obtain most of my information, including the in-depth process involved in the various advantages and disadvantages, because I believe it to be the most unbiased source out there. Because it's not tied to any specific company, it will weigh the disadvantages along with the advantages in an unbiased fashion. Of course, now it's not wise to take all the information from one source, and so I utilized other sources as a backup to ensure my information is accurate and well-rounded. The rest of my sources are from pages directly tied to casting companies, which I thought may not portray the downsides of vacuum assistance quite as well, so I use these as strictly confirmation of my original data rather than a main source. I hope this presentation has been eye-opening for you all, and I hope you take my suggestion into consideration, as I believe this will have an astounding impact on our workplace here at the Imaginary Company. Thank you.